Hey guys, this is 18.1 Introduction to Acids and Bases. When you finish watching today's video, you should know the difference between the chemical and physical properties of acids and bases. You should know a few terms related to acids and bases and that are able to identify them. And you should know the three main models of what an acid or a base is. Let's look at the physical properties first. Acids are going to always taste sour. Bases are always going to taste bitter. Now, both an acid and a base will conduct electric currents, but a base also tends to feel slippery to the touch. That means that most of your soaps that you feel, those are usually bases. Now, when we talk about the chemical properties, we're going to focus specifically on how these things change litmus paper. So acids are going to take blue litmus paper and turn the paper red. Bases, however, are going to take red litmus paper and turn it blue, so they're the exact opposite of each other. Now, the only extra piece of information that I have on this slide is the little diagram or the drawing here, and it also will tell you that an acid will react with some metals to produce hydrogen gas, and that dissolved carbonate salts will release CO2 when reacting with an acid. So if you ever are wondering if something is really an acid, you could take it and react, and if the metal produces H2 gas, then you know you have an acid, or if you have the carbonate salt and it produces CO2, you also know you have an acid. Now we get to a few terms specifically used to identify and talk about our acids and our bases. The first two are actually interchangeable with each other, and when you refer to one, you could use it for either or. That would be our hydrogen or our hydronium. Hydrogen is an H+, and hydronium is H3O+. Notice that they're both positive charges. When you have a hydrogen or a hydronium, they're both really focusing on the extra hydrogen, and this hydrogen has given away its extra electron, so it's just really a proton. And the hydrogen that's floating around, when we say hydrogen, it's just referring to the hydrogen alone. And when we talk about hydronium, it's like a water that's accepted that hydrogen atom, and so it's H3O, but it's still got a plus charge. Now, the opposite of this is going to be our base, and that's going to be referring usually to the OH group, or our hydroxide. Notice that our OH group is negative, and that's because it's got an extra electron than it would have normally had. So this OH group is always negative. Now, to have an acidic solution, you're going to have more hydrogen or hydronium than you will hydroxide, and that's how you know that you have an acidic solution. To have a basic solution, you're going to have more hydroxide than you would have hydrogen or hydronium. Now notice that this diagram, you have two waters and they're reacting together. This is a reversible reaction, so you notice that you have double arrows. But in this case, the two waters are reacting so that the one water is giving one of its hydrogens to the first water. And that will form a hydronium ion, which you could also refer to as just hydrogen, and ignore the water part and just focus on the hydrogen. This side is always positive, remember, so the hydronium is positive. The other side, we have the OH that was left over, and it's going to be negative, and that's our hydroxide. Now we're going to talk about the Arrhenius model. This is the first of our three models that we're going to use to describe how acids and bases form. So Arrhenius model is the first one, and for a long time people were dealing with acids and bases and they were noticing things, but they never quite had an accurate definition that could categorize all of the different things they knew to be acids and bases as either an acid or a base. So Arrhenius model is the first one that's going to try to sort out what's the difference between our acid and our base. In this model, we say that the acid contains hydrogen, and it will ionize to produce hydrogen ions in an aqueous solution. So it has to have hydrogen originally so that when it goes into water and becomes aqueous, it's letting go of that hydrogen, and the hydrogen is freely floating around. Remember that before we said that the acidic solutions are going to have an excess of hydrogen or hydronium. Now, in the Arrhenius model, he's going to describe a base as something that contains the hydroxide group so that when it is put in water and it separates and dissolves into an aqueous solution, it's going to end up having an OH group floating around, which is our hydroxide. So notice that's the difference between the Arrhenius model and the Arrhenius model acid and base. One is going to produce hydrogen in solution, or hydroxide. The other is going to produce hydrogen or hydronium. The other is always going to produce hydroxide. Notice in this example for the acid, you start with HCl as a gas, and it splits apart into hydrogen, which is positive, aqueous, plus chlorine, which is negative, aqueous. So notice that the HCl is able to split apart to donate or to give a hydrogen. So what it has to do is it has to be able to give hydrogen to the solution. So HCl is considered an acid because it's giving hydrogens. Notice in the next example, we have NaOH, and this has the OH group. When it splits up, you're going to have a positive sodium and a negative OH, which is our hydroxide. So notice that that is donating or giving the OH to the solution. So that is going to be considered an Arrhenius model base because it's giving up OH. The next of our three models is the Bronsted-Lowry model. Now this is actually named after two separate scientists that work together. And in this model we have the acid is called a hydrogen ion donor. That's exactly the same as what the Arrhenius model said. The only difference here is that in the Bronsted-Lowry model they're trying to simplify things, and they said that not every acid or not every base is going to have an OH group to donate. So they wanted to try to be more inclusive and include more things in the base category. So they said that instead of being an OH, something that will give up hydroxide, all they need to be a base in the Bronsted-Lowry model is to be a hydrogen ion acceptor. So the acids will be hydrogen ion donors, and the bases are hydrogen ion acceptors. And that's all they really care about in the Bronsted-Lowry, is where the hydrogen is going to go. Is it going to be accepted or is it going to be donated? Now, as a result of this, we're going to have our conjugate acids and our conjugate bases. With a conjugate acid, it's literally the other side of the equation in a reversible reaction. So you notice how in one way, in the forward direction, you would have reactants becoming products. That's always going to have in the forward direction, you're going to call your acid and your base, that's just named acid-base. But on the opposite side, the products, those are going to be considered your conjugate acid and your conjugate base. And so they will be the ones that are in reverse, the acid or the base. The conjugate acid excuse me, was the species that's produced when a base accepts the hydrogen ion. So this is the base, and now that it's accepted the hydrogen ion, now it will have the hydrogen, and in the reverse reaction, it's going to be the thing that donates that hydrogen, so it's now considered the conjugate acid. Now the conjugate base was originally the base in the original forward reaction, but now it doesn't have the it hasn't accepted the hydrogen. It's instead going to be the one that is going to donate the hydrogen because it took that hydrogen in the first place. So notice that water is always an acid and a base because it's always going to be able to either take or give hydrogen, because if it takes the hydrogen, it'll turn into our hydronium, and then if it gives an acid, it'll turn into hydroxide. So water is both an acid and a base in the Bronsted-Lowry model, and that's really important. Now we're going to look at this example because I know that the Bronsted-Lowry labeling conjugate acid and base sounds a little confusing until you really see it in action, because it really isn't as complicated as it sounds. So notice the first example, you have HX, aqueous, plus H2O, liquid, double arrow, which means reversible reaction, and you're going to form H3O, aqueous, plus X, negative, aqueous. Now, look at the reactants first. Which of those two things is donating the hydrogen? Now, they both have hydrogen, but which one is actually going to give away the hydrogen in this forward reaction? Alright, now that you've answered that, I hope that you said the first one, the HX. That is the one that's giving away the hydrogen, because you notice that when we started, we had HX, but when we end, the X is all alone. So it had to be the HX that gave away its hydrogen. So that means that that is the acid. Now, if this is the acid, the other one must be the base. So in this case, the water is actually acting like a base because it's going to take on the extra hydrogen. You can prove that because it became H3O. So it was the thing that accepted the extra hydrogen. Now, look at the reverse reaction. If you start with H3O and just X minus, which of those two is going to be able to donate hydrogen in the reverse direction? And again, the only one that's able to donate hydrogen in the reverse reaction is the H3O, because it's the only one that has hydrogen. So that becomes our conjugate acid, because now it's acting the part of an acid, being the one that's going to donate the hydrogen. And so that means that our X minus is now our conjugate base, is the one that will accept the hydrogen back. So that was only going to be happening with forward and reverse direction equations. Notice this is a summary statement with the Arrhenius, Bronsted-Lowry, and the Lewis models. So notice that the Arrhenius focuses on H plus and then OH, and the Bronsted-Lowry only cares about H plus, but it's going to be a donor or an acceptor. Now as we go into the Lewis model, you're going to find that we're going to not even talk about hydrogen anymore. Instead, to be more inclusive, Lewis is going to focus on electrons and is going to have an electron pair donor or an electron pair acceptor. So the Lewis model, if you remember, we drew Lewis models when we were working with our covalent bonds, and those are the diagrams that have all of our free electrons around the centralized atom, and it's going to show all of our single bonds and double bonds with lines. Alright, so Lewis is going to try to be more broad even than the Bronsted-Lowry model. He's going to be able to try to categorize any acid or any base, whether it has hydrogen or doesn't have hydrogen. So he's going to be very inclusive with his definition. And so he's going to call anything that is an electron pair acceptor, that's an acid, because it's accepting electrons. Anything that is an electron pair donor, that would be considered a base in the Lewis model. So notice our examples here. We have BF3, and we have another fluorine floating by trying to come. Now notice how the arrow is going from fluorine to the boron. So which one is donating the electrons? And if you look at it, the fluorine is going to donate electrons to boron. So because the fluorine is donating the electrons, fluorine is considered your base. And because the boron is accepting the electrons from fluorine, it's considered your acid. Now the next example, you have NH3, and notice the arrows taking the dots from NH, or from the nitrogen, and drawing them to the H+. So notice that the nitrogen in this case is the one that's donating the electron, and the hydrogen is going to be the one that's accepting those electrons. So in this case, the hydrogen is my acid, and the N for my nitrogen is my base. And that's all that the Lewis structure really is caring about. The Lewis model is just figuring out which one's accepting and which one's donating those electron pairs. Alright, now that you've finished this video, you should know the difference between the chemical and physical properties of acids and bases. You also should know some terms dealing with acids and bases, and you should know the three main models on how to categorize your different acids and bases.